Okay, so voltage is the first thing we're going to talk about. This is the electrical pressure that causes electrons to move in a circuit. Something has to start those electrons moving. Otherwise, they're just going to stay there, right? Your table has electrons in it. My mouse that's sitting here on my computer has electrons in it. The computer has electrons. Everything's got electrons in it, but nothing happens until something tells them to move. It's the voltage that does it. If I put 12 volts to something, those electrons are going to move. I put 50 volts to it, and they're going to move faster. I put 100 volts to it, they're going to move a lot faster. I put 1,000 volts to it, and they're going to burn up, and it's going to turn into a big fire, right? But voltage is the electrical pressure that causes the electron movement in a circuit. It's referred to as EMF, electromotive force. It's measured in volts. An E or a V is used to designate voltage. So voltage is the pressure that gets things moving. That brings us to current. Current is defined as the rate of flow of electrons. This is the measurement of the number of electrons passing a given point in a circuit in 1 second. All right, so I don't know if you can see this right over here, but that 6.25 times 10 to the 18th electrons per second. That's 1 amp. 1 amp. So I want you on a piece of paper to put 625 and then 16 zeros after it. Then I want you to go every 3 numbers and put a comma there and look at the number that is the amount of electrons that move past 1 point in 1 second for 1 amp. Pretty huge. All right, so it's measured in amperes. We say amps. And we use an A or an I to designate amperage. All right, Y is I. I is for intensity. Right? Before we had volts, it was a V or E. E is electromotive force. A or an I for amperage, and I is intensity. Talk to anybody that's been zapped, and it's the amperage that gave them the zap. They'll say that's pretty intense. So now we have the final piece to this, is resistance. It's defined as the opposition to electron flow. It is measured in ohms. An R or an omega sign is used to designate resistance. The opposition for electron flow. Now, what I like to do is I like to say, can we put voltage and ground, 12 volts and 0 volts, in the same place at the same time? And you're supposed to say, yeah, maybe. And then I will go get a booster pack from the back of the room, and I will say, well, let's see what happens. And I take the positive and the negative from the booster pack, and I touch them together, and sparks go flying through the classroom. And then I say, nature said no. Okay, so we need to have something between the voltage and ground, the two sides of a circuit. Otherwise, we have a short circuit that blows flames, pops fuses. Okay, so we need something in the middle that's going to be the what I call the battleground between the two sides, and having a load, a light bulb, a motor, anything satisfies the load. That is the resistance. Okay, it's the opposition to electron flow. Now we have some characteristics that determine resistance. First, the atomic structure of the material. If I have a piece of red wire and I decide to replace that wire with a piece of shoestring licorice, do you think it would work the same? Probably not. I don't think it's conductive. Okay, so obviously what it's made out of is going to define whether electron can flow or whether electron cannot flow. The length of a conductor, okay, how long something is. Well, when we have wire, if we're going to go so far, let's say I wanted to go 100 feet. Obviously, I would lose as I move through that wire some of my voltage that I was carrying. So I have to take it and make that wire bigger. So the longer we go with a conductor, the higher the resistance gets. Number 3 is the diameter of the conductor. Okay? The size of the wire. If we have a really small wire, obviously we try to put electrons through it and they rub because they can't fit through it and they cause heat and resistance. If we go to a bigger wire, we can put more through it. When we're talking about electricity, I want you to think about water in a pipe because they have the same characteristics. They act the same way. So if we had a pipe and we had a small pipe like a straw from McDonald's and you tried to put a gallon of water through it, how hard would the water come through? It wouldn't, right? It would sit down and it would fight and back up and wouldn't go through it. But let's say, I don't know, we took a pipe that goes through the sewer and try to put a gallon of water through it. It just goes right through, right? So the diameter of something decides how easily something flows through it. The temperature. Well, if I was in the classroom right now, I would show you a light bulb and we would measure the resistance of the light bulb and then we would plug it in and light it up. But we can't measure the resistance of something when it's working. So we would have to calculate it. This is when I'd introduce you to Ohm's law, which we'll do later. But this would be a perfect time to do it. And we'll discover that resistance goes up with temperature. So the hotter something gets, the higher the resistance goes. Number 5, the physical condition of a conductor. So if I take your radio out of your car and stick it in the ocean, salt water, how do you think it would work afterwards? Probably not so good. Therefore, I think that it might not work so good. And if it doesn't work so good, then electricity doesn't flow through it so good. So the resistance of it must have went up. So if something is in terrible condition and covered in corrosion and yuck, resistance goes higher.